this presentation module, we'll talk about VLSI testing versus hardware security or hardware trust. We'll try to understand whether there are any similarities between these two concepts or these two areas. As we all know, we've been testing these chips for decades, so VLSI testing is a mature field in terms of the research field, but on the other hand, hardware security and hardware trust is more of an emerging kind of a field because the community has been concerned with the threats relatively more recently compared to testing. In testing, we defend against faults or defects, and in hardware security and trust, we defend against attacks. So a natural question to raise is, are there any similarities, or are there any differences, radical differences in terms of approaches? So this is what we talk about next. Let's first understand the IC manufacturing process so that we have a better understanding of what VLSI testing tries to accomplish. In IC manufacturing, we start with a silicon material, and then it's sliced into wafers. These plate-shaped wafers then are exposed through a mask to UV light, and then a pattern is engraved on these wafers. And it's actually the replicas of a pattern that is engraved on these wafers, which is done through this mask. This mask, photo mask, embeds the design information. So all the design effort that designers spend goes into this mask, which represents the physical design of the chips that will come out of this process. And after this step, which is also called photolithography, it also involves, after the pattern is engraved, involves chemical and mechanical steps. There is the dicing step, and we get individual dies. At that point, we need to test the die to see whether the die is defective or not. And then we identify the good dies, and the good dies go into packages. And after packaging, we get the integrated circuit. At that point, we need to test the final part again, just to make sure that the packaging did not introduce any additional defects. And then the chips are ready for shipping out to customers. Now, as you can see, this process involves many mechanical processes such as slicing and dicing, and also as well as steps such as photolithography or chemical steps, etching process. As a result of these steps, the chips may end up having certain defects. At the physical level, we could be talking about bridging kind of defects. We can talk about a dust particle on a mask creating photolithographic kind of defects. We can talk about alignment issues and defects resulting from these issues. So defects are a natural end result of the manufacturing process being imperfect. And then, over a few runs of iteration, things get better. We get fewer and fewer defective chips being produced. But until then, test is a crucial step to not only identify the defective parts, but also to improve this process to get more yield, to get a better yield. These defects at the electrical level result in problems such as a transistor that is always stuck on or stuck open, regardless of what values you apply to the transistor, or we end up having resistive shorts, resistive opens that are basically slowing down the chip and degrading its performance. So, end result of these effects at the electrical level, we have failures at the system level. We can talk about chips that simply don't work, or we can talk about chips that work, but they can only operate at a slower speed than they were intended to operate. We call them performance failures. The first class is called catastrophic failures. So obviously, all the chips, every single chip needs to be tested to see whether the chip is working properly, it's working at the speed that it has been designed for. But of course, we've been testing chips for decades. Ever since the first chip came out, we had to test it for defects. So the community has been working on developing nice fault models that represent physical defects. By using these fault models, community developed software tools. There are actually major EDA companies that provide these software tools to design companies. These software tools help generate test patterns for a given design based on these fault models, and these patterns, when applied to the manufactured chips, will help screen out the bad chips and throw them away, and basically make sure that the good chips are the ones that are shipped out to customers. Now, this concept, can any of these principles, can any of these concepts be leveraged for the trust domain, hardware security and trust domain? Can we adapt any of these techniques? Before that, we need to really understand also the differences between testing and security. In testing, we're dealing with defects, which are natural phenomena. But in security, we're dealing with malicious and intentional attacks. So there's a human factor there. So in testing, yes, we use fault models to represent these physical defects, but can we talk about attack models? Can we really model the way humans think and they can possibly attack our chips? So that is one distinction, dealing with natural phenomena versus intentional attacks. We talk about detecting faults. Of course, we can talk about detecting attacks as well. We can also talk about preventing attacks if we have defenses in place. Scaling challenges, we have these challenges in both domains. Chips are getting more and more complex. The gate count is continuously increasing. So whatever solutions we come up with, we expect them to be computationally scalable. In testing, we're really dealing with fault models that are static in nature. Once we understand the physical defects in a particular technology node, then we come up with the mathematical and the fault models that represent those physical defects, and we typically stick to those fault models. So the typical fault models in testing are stack-gap fault models, transition fault models, and detect. So these fault models are basically representative of most of the expected defects that you get in chips. But in security, the attack models, if you can develop those, they're not going to be static in nature, because every time you develop a defense, human beings, the attackers, will try to bypass that defense and will try to come up with another attack. So it's going to be more dynamic in nature. In testing, we can talk about fault coverages to define the quality of our test. 99.9% stack-gap fault coverage, for instance, may be sufficient for our chips for a particular application. But can we talk about attack coverages? 99.9%, would that be enough? Because you'd be leaving 0.1% of a hole there that could be exploited by the attackers, and that's all the attackers need to find that hole and exploit it. So it's trickier to talk about coverages in the context of security and trust. There is also the concept of defense. In the testing domain, to test every single chip, of course, we spend time on expensive testers, so there's a cost associated with it. It's a recurring cost. And there's the quality, of course. If we spend more time, we can test it better, so we get fewer test escapes or higher fault coverages that define quality. So there is this cost versus quality trade-off in the context of testing. And if we can insert certain defenses in place, which we refer to as design for testability hardware, SCAN is the most known solution. For instance, turning every flip-flop into a fully accessible unit and then connecting them into chains that we call scan chains. So approaches like that are referred to as design for testability, and the idea is to push the cost versus quality trade-off favorably. So for a given cost, you get better quality because of DFT, or for a given quality, you get lower cost because of DFT. That's the idea behind design for testability. In the context of design for trust, can we do similar things? There is obviously, again, the cost versus quality trade-off. Can we push this trade-off curve favorably to be able to expose or even prevent the insertion of Trojans, for instance, or to detect counterfeit components, or to protect design IP? So, is there anything that we can learn from DFT and apply in the context of design for trust? So in this module, we talked about test and security. We compared them to understand the differences, and we also tried to figure out whether there anything that can be borrowed from the mature domain, which is the VLSI testing domain, and can be leveraged in the context of hardware security and trust. Thank you very much for listening.